Okay, so welcome to the third day of the workshop. I will not introduce myself again. This was already done yesterday. I introduced myself, and the day before yesterday, I also introduced myself very broadly. So, welcome everyone. I am Matthew, and today we will be discussing some more quantum, let's say, quantum computations. Since previously we have been talking about the mathematics very heavily, so today we will be doing this only briefly for very simple operations, and we will be tying some of the quantum world representations to our classical representations that we have discussed yesterday, because there is a difference between these two, and I have already told you about some of the differences yesterday uh, at the last hour, I believe, and this was the representation of the states. So, but first of all, let me discuss which notebooks we will be using for today's lecture. So we will be using a Quantum with Qiskit folder. Uh, so you could navigate. I already have opened my Jupyter Notebook session. If you don't know how to do this, you can watch the previous lecture. Basically, what you do as a very quick recap is that you activate your notebook, you activate your environment, and then you type in Jupyter Notebook with Notebook dir if you are in some other location. For example, I have the C users ADM location, and if I want to open a specific directory, I could do this with the parameter Notebook dir. That's how I do it. And I do every single thing that I have just described inside of the Anaconda prompt. This is the prompt. This is the application that comes with Anaconda once you install everything from the installations instructions that were attached to our Bronze Qiskit repository. But without further ado, let's jump into today's lecture. So we have been talking about different states. I will open up a paint and I will also minimize this window on my side, since this is not really necessary to be here. And I will start explaining. A little bit of recap from yesterday. We have told that the classical representation had this very nice thing of being encoded in binary. Once we have a system with just two decisions to make, let's say a rainy weather or sunny weather, this can be represented as 0 or 1. We could use our tensor product to combine many of these single bits into a composite system that can express way more than just two decisions. It can express 4, 8, and so on, as the tensor product dictates us. So for example, when I combine a 0 with yet another 0, I get a 0, 0 from a classical system. And this is roughly a column vector with now four vector components, since these were two component vectors. I also drew the analogy to what we will be discussing today. I have started this at the last mm, hour of the lecture. that what we do in a quantum compared to what we do here, right? So here was a classical system. Notice that we draw this rectangular L to surround our bit representation. Uh, there is an info in the chat. About the keyword opportunities, there are some initiatives that you could that you can be a part of, and one of them is QIntern, and probably Pavel can or any of the mentors that are here today with us can post a message about this inside of the Discord channel.
I will share a link. Indeed, there is a QIntern program, but this year's edition has ended. So
Yeah,
we had a final demo day in August, but there will be the next edition in the next year, hopefully. So the idea is that
yes.
senior researchers from all over the world can submit their ideas for research projects, and then students from all over the world can apply. And as keyword, we match them. So we match the senior researchers with the students or quantum enthusiasts, and then during the summer they collaborate for several weeks, and there's a demo day with the presentations of the results at the end. So that's the idea. But of course they can continue their collaboration if they are satisfied and still interested uh, in the research. Yeah.
Okay,
So
my internet is
yeah, this year
stable.
we already had the sixth edition of the Quinten program. So the next year will be the seventh, hopefully.
Okay, so yeah, so to recap what Pavel has said, follow the link and you can find out the topics of this year of this year's subjects. You can follow the researchers that were listed on there. And yeah, let's go back to the lecture. So that was a short recap. Now, what we could, oh, okay. So as I said, this is the classical representation. What about quantum representation? What we have said is that we no longer draw these like L's, square L's, but we draw kind of like a bar. We express our bit and we finish with the sharp, let's say, uh, greater than sign. What is this notation? This is a cat notation. So this expresses that we also have the same situation as here, but now this vector represents a quantum state of 0. We also do have the our regular notation with the linear combination of two different states, right? So we have some chance alpha of our now qubit being in a state 0, or we have some chance beta that our qubit is 1. So the one state is 0, 1 now. And all of this state is represented as Xi. Now, what are these alpha and beta? These are amplitudes, and this is one of the main differences that I tried to explain to you yesterday. So we no longer express our vector as something like this, that there are, for example, wait, let me switch the color to denote the vector of possible states. So for example, we could have 0 0.4, 0 0.1. This is 0, and I've written some squiggle. 0 0.1, 0 0.3, and then it turns out to be 0 0.2 is the last member. So all of these entries sum up to 1, right? But this was classical representation. What do we do in quantum representation? The alpha and beta are no longer real valued, let's say, probabilities. What they are is the amplitudes that express the state of the particle that we operate in. And then these amplitudes have to be squared back to obtain the real probabilities of getting the states that we can obtain after a measurement. So for example, here we could say that if we wanted to express it as, in quotation marks, 0.5 and in quotation marks 0.5, this had to be squared to actually be 0.5 probability. So what we do is we represent it as 1 over square root of 2 instead. And these vector components do not sum up to 1. So they no longer sum up to 1. This is very important difference, one of a few that we would be dealing with while operating on these states and while performing calculations on quantum computing hardware. This is the most important one. We cannot really express the probabilities in a standard way. We have to express them as a, let's say, square root of probability. And these are amplitudes, right? So that's that. It is exactly the same when we want to express a tensor product of two different qubits. For example, I have a qubit that is alpha and beta, right? And then I have yet another qubit that is quite different. And it had some yet another operation performed on it. Then the combined state also is represented by amplitudes, and so on and so forth. So no matter the amount of qubits, that's our representation right now, the amplitudes. That's what I want you to know. So that's one of the differences. I have told you about the different gates as well, right? So what, uh, sorry. Okay. So I told you about different gates, right? So one of these gates, or even two of these gates, you already know. So okay. Let me compress this notation slightly. And I will show C here equals this. So we knew two gates, or rather operations, from our classical representation. We know the identity. Oh, sorry, you didn't see that. So there is an I, right? And there is a not operation, which was kind of the same, so diagonal, but on the other axis. So these matrices are compatible with our quantum representation. But what about something else? If I wanted to go from a state that is, let's say, zero, complete zero, like 100% chance of zero state and 0% chance of state one, right? So this would be our Xi now. How can I get to the state that will be like 50-50, let's say? Well, in the previous case, what we had classically was the matrix that we expressed with 1 over half, 1 over half, 1 over half, 1 over half, and this was the this is the transition matrix that expressed a fair coin, right? Fair coin. Well, okay, so can we do it here? Well, the answer is not really, because what we deal with is exactly what I have told you a minute ago, that what we want is to represent the states as amplitudes, right? Not by real valued probabilities. We do not deal with this anymore, right? What we deal with is amplitude. So what do we need to actually express this transition into the quantum 50-50 state? Well, it turns out that there is an answer for it. So let me encode this matrix as F, meaning fair coin. So kind of like a fair coin in quantum, we would express it as the same thing that I had told you also a minute ago. So when we expressed our 50-50 as a quantum state, we use this 1 over square root of 2, right? So this would be a quantum 50-50. So this is Xi0, and this is Xi1. What we do to end up in this state is use a matrix that would be filled with 1 over square root of 2, right? Then, if we want to have an equal chance of having either state 0 or state 1. So we could start with something like this as our answer, right? And this would be very, very, very close to our answer. But we need something, but we need one more thing, which is a minus here. And this is because we would like this, this calculation to be reversible. And it turns out that this gate, this operator has its own name, and it is called a Hadamard gate. This, oh, there are some mentions, but let's not diverge from it. So this gate is a Hadamard gate. What it achieves is exactly what we have said here. So it it allows us to transition from the state 0 into our, let's say, fair coin flip state. And we can explore it in one of the, oh, actually, let me clear everything. We can explore it in our Q20 Jupyter notebook. By running one of the first cells that is available in this notebook. So recall that what I have told you yesterday is that we always start from the state 0. And recall that yesterday when we applied an X gate onto our qubit, right? I will open up my PyCharm as well. And let me also open it in the presentation mode. So what we have is we had 1 qubit. This was enough. Let's comment these out. Run the circuit again. I think there will be no errors. Yes. So what we have is, oh, I have, yes. So what you can see here is that we always get a state 1, right? But after applying an operation that will be encoded as H here, so this will be our H gate, we now see that we get a situation that sort of resembles our coin flipping, right? And this is exactly the operation with this 1 over square root of 2, 1 over square root of 2, 1 over square root of 2, minus 1 over square root of 2. This is the operation that leads to this result. So you can not only have a single deterministic outcome from your quantum computation, but you can have some sort of probabilistic distribution of 0, 1, or maybe 0, 0, 0, 1, and so on. And each of the experiments, each one of the shots that you do performs a yet another experiment that will end up in either 0 or 1. And what your quantum simulator will do is it will sum up these results. So for example, let's say I have shots 1. So here I had only 0, 0, 0. Oh, maybe. Oh yeah. So here it is. Now it landed on 1. But if we manipulate the counts, then we have then we will have some distribution of this. So yeah, this is one of the consequences of applying this gate. Let me see what we also have here. So this is the gate that we apply, H, and then we perform a measurement. Here is when you execute this cell from the notebook Q20, you will see the graphical representation of operations that we are doing. So we first, on the entire quantum register, reg, we first apply the H gate. This is the box that you see. in here, right? And then we measure. I will note this with M. And then we store the result in a bit 0 of our classical register. So this is C register. Okay. So that's one. So that's one of the operations that make it slightly more interesting. What is the what can be said about this operation? Well, we could say that we have some sort of situation as if we have applied a beam splitter onto a source of photons. And the resulting operation yields us a split of 50% in one detector and 50% in yet another detector. So here we also have in yet another cell. After we perform this calculation, wow, that takes long. Wow, I think something has happened with my notebook. Let me try out another. Yeah, I think I need to restart. Um, okay, let me see if this helps. Right, yeah, I think it will be better if I do this instead. Or I will do this. Okay, so it had some error that it couldn't process. Uh, it seems so. Okay. Yeah, so now it works. So let me get back to our this and this. Yeah. So this is another yet another thing that I have told you that you could do with Qiskit. For if you import a plot, a histogram plot from their visualization package, you could display your observables as kind of like frequency plot, just like that, by in a bar chart. This is a very nice way to color. Let's change it as a green. Yep. As we have observed after this implementation constant probabilistically. So what about two flips? Now situation is slightly different than what you would expect at the face value. So what we can do is we can chain gates. And this is how we, let's say, extend our circuit and append more instructions one after another. This is the other way, and it actually has in the inside of the Qiskit, you actually have the possibility to do exactly that. They have these operations that have append. You could define your own gate. and or some sort of, let's say, uh, you could do, let's say, yet another set of operations and append onto the quantum circuit this set of operations. But here we just invoke two different instructions, which are both expressed by the same transformation. And now what? What will happen? Well, what we get is zero state again. And this is quite different than what you might expect, because what you would expect from quantum flipping is that you probably have like, okay, I flip once, I flip two, I flip twice, I flip thrice, and so on, and the distribution doesn't really change. But here, what we manipulate ultimately is the quantum state. So every single transition matrix is kind of like a transition from one state to the other probabilistic state, the other distribution. And doing this tells us that, hints us at a possibility that our Hadamard gate might be its own inverse. And this is exactly true. But we will explore this slightly later, but this is our result. So it can be quite bit disturbing at first, but this is a normal behavior. I would be quite a bit let's say worried if this wasn't the case. But yeah, that's a real result. So so later on, it's not that the probability couldn't sum up to one, it's that amplitudes do not sum up to one. The probabilities are. And what we do is that, let's say here in this notebook in Q24, if we describe it as alpha ket 0 plus beta ket 1, these are the amplitudes. And what is true is that the amplitude square sum up to 1, right? Because these alpha is in our quantum coin flipping is square root of 2, beta is 1 over square root of 2, but after squaring, both become 0 0.5, 0 0.5, which sums up to 1. Does that clear? Yeah, for sure, no problem. So here in Q24 with 1 qubit, what we apply is the transition matrix, our first one. We already talked about this one, and this one is the X gate or not operator. I will expand on it slightly further out, but this is one of the operators that we can apply, and it is pretty much, we could say, deterministic, because what we do with this operator is we just flip the state 0 into state 1 pretty much from 100% 0 to 100% 1. However, this isn't always true, and we will explore this slightly later on in today, slightly later on today, why this shouldn't be the case that we view it as that. So here's the Hadamard operator. As I have explained to you, we have 1 over square root of 2 exactly because we deal with amplitudes instead of regular probabilities that could be explained by real numbers, as in our standard probability explanations. And what we see here is that when we apply the h to our xi, which in this case our xi is just explained as 0 because this was our initial state, right? We obtain some state c1, which in this case is 1 over square root of 2, 1 over square root of 2. And this is exactly this result. And as we have explained previously, as we have shown previously in PyCharm, this is what we end up with, right? These counts do add up to 100, but these are distributed between the result 1 and result 0 that we observed during measurement. And this is what our classical register recognized after the measurement operation and after the result has been stored in the classical register. So what about something else? Let's say that I apply two different operations. First, I apply onto our quantum circuit, I will apply an X gate operation, and then I will apply an H gate. What will happen? Oh, index. Right, because I have only one qubit, so I shouldn't use a 0 here. So it seems that maybe let's increase the number of experiments so we can see it clearly. 10,000. Okay, so it seems that we have pretty much the same situation. So even after I apply X gate at first, because remember when we apply the X gate, this is what we do now. We start from state 0, which is our C0. Then we apply an X gate, so we land on 1. And then we apply our H gate. So what will be the state here when we apply an H gate from the state 1? Not from the state 0, as we have previously done, because this result is 1 over square root of 2, 1 over square root of 2. I'm sorry for the squiggles. I will. Oh. So what will happen here? Recall that I said when we have 0, 1, we can copy the second row of the matrix. But what is the second row of the matrix? The second row of the matrix in Hadamard is this one. So it now changed my size. Okay. I have no idea how gates are represented in a physical quantum computer. This is proper. Yeah, I do not really know because there are so many different vendors of quantum computing hardware. Like you have IBM, you have D-Wave, you have Quantinuum. We have, for example, now recently what I have seen is Alice and Bob. This is actual company that's how they name themselves, and they also have quantum hardware. Uh, I do not really know how do they represent an actual gate on their own quantum hardware. Uh, this isn't really hardware agnostic. There is a standard for representing a quantum computation universally, and this is a format called QASM, which means quantum assembly. But is it widely adopted? Well, I wouldn't think so because everyone wants to be the one that use their quantum hardware, right? And since some people, even from like Alice and Bob, the quantum hardware that I have just read about 2 days ago, they have something like hardware baked quantum error correction. So they have some sort of like embedded qubits that you do not see and you do not interact with from computation that weave into the actual quantum error correction code. So what they do is that they translate your, let's say, Hadamard gate into their own representation of their own hardware. I do not, I cannot really tell you how this is represented. Uh, I don't think I have a satisfying answer for that because this could be hardware. This is not hardware agnostic. Yeah, this is what we do is pretty close to quantum assembly, but it is more like quantum C language. This is what we are doing here. This is not exactly the quantum assembly that okay, we do the gate, let's say that is called something, and this something is yeah, exactly what Łukasz says in the chat. Yeah, so okay, so back to the lecture. What we have is what we have here is as we have said, when we start from the state 0, we'll increase the thickness. When we start from the state 0, we end up with, after the H operator, we end up with 1 over square root of 2, 1 over square root of 2. However, when we start from state 1, something different happens. Because we copy the second column of the operator. And after applying Hadamard, what what is the result? Well, 1 over square root of 2 and negative 1 over square root of 2. Is it actually correct? Well, in terms of our computation, it actually is, because what we care about ultimately is that our squares of amplitudes sum up to 1. This can be amplitude, can have a negative sign to it. So that is also very important distinction from the classical operators and classical representation. that we can actually have some sort of, in quotation marks, negative probability. Uh, in here, we say that this is negative amplitude. And these states have, since they are pretty special in quantum computing, these states have their own representations and encodings. Let's say encodings. The one that have all positive entries, so 1 over square root of 2, 1 over square root of 2, is called a ket plus. So it is represented as the ket notation with the plus inside. And the other one that has a minus in the bottom is a ket minus. So these are two kind of distinct states, and it's really nice if you memorize it, because it would be easier for you to recognize what happens. Okay, so let's jump into the Q28. I kind of jump with the material because I have spent a lot of time on the introduction, and what I would like to tell you today is with also a generalized version of the operators. Here we have so far spoke about identity, about not operator, which is called X, and about Hadamard operator, which was quite like kind of like quantum coin flipping, right? And then there are generalized operators that can allow you to obtain many different states that you probably would like to obtain. So that's why I'm kind of speeding up with the material. But so far, this should not be very complicated for you. I think. So here at Q28 notebook, we have some more uh, some slight expansion onto the idea of a quantum state. What we have is an expansion on what can be a quantum state and what cannot be a quantum state. And what cannot be a quantum state? Exactly as I said before. It all comes down to the same formula, which is alpha squared plus beta squared is equal to 1. If the state cannot be expressed with this equation, it is not a valid quantum state. And it cannot be obtained during a calculation or initialization step. Because we could initialize it, we could initialize our calculation to say that, okay, this is my, let's say, in business problem. I start from this state because from my real world function, this is what this is what is right now. And now I have to transform somewhere else to describe my solution of a business problem. So I could initialize it in certain state and then start a calculation from that spot. So if we cannot express it with this formula, this won't be a valid quantum state. And these states are not valid because when we see that 1 over 2 is the amplitude, once I take a square root of this, I will have the sum. This is, I think, 0.7 something. The sum will equal to 1.4 or even more. So this is not a valid quantum state, and I cannot express it, or I cannot obtain it on the quantum hardware. Here is a note that whatever quantum state we do, whatever quantum state we would like to express, what we can also do is a norm of that vector in space. Since recall our first day, what we say is that alpha squared plus beta squared is equal to 1, but 1 can also be expressed as a square. And all of this is pretty much like a Pythagoras theorem. And this also is true, and it is true, and it has to be true in more than our oh in more than oh God, I have messed up with my okay. This is, I think, what yes. We can express it in more than just 2 dimensions. This is 2-dimensional case. What happens if we have more than just 1 bit, or in this case, 1 quantum bit? We could also calculate the proper state representation, and then come up with uh, proper initialization for that state for more than 1 qubit. Here, for example, we notice the quantum state that has 5 entries. And what I would like you to do is to calculate it, if it is correct or not. First, it has a missing number, which is A. And in Q28, in quantum state, in Q28, which is the notebook that we are now in, we could calculate this A to find a missing proper number that we would fill in to have a proper quantum state. So I would like you to do this exercise now. I will leave you for about 2 minutes. Try to come up with the answer for yourself. And then we will be back. And then I will be back in 2 minutes. So post an answer in chat. For example, with the fraction, let's say this would be 0.9, like this. You could also say like A equals 0.1, right? It's up to you, but try to come up with this answer, and you could answer it in the group chat. So I will give you 2 minutes. Okay, so I am back, and now I see a couple answers. So how do we come up with this answer, with the correct answer to this problem? Recall that for 2 bits, for those that didn't manage to do, for 2 bits we have, for 1 bit, I'm sorry, uh, you have an alpha and beta, which are amplitudes, and it is their squares that have to sum up to 1. And what I told you as well is that no matter the amount of these amplitudes, we could have alpha, we could have beta, we could have gamma, we could have many, many, many others, all of them to represent a valid quantum state, all of them has to be equal. The sum of squares of these amplitudes would have to be equal to 1 as well. So let's do a quick program. So what we have a list of amplitudes, which we see as negative 0.1, negative 0.3, 0.4, and 0.5. Oh, and each of them is a single amplitude, but it isn't a squared one. So for each number, for each amp in list amp, when we sum up every single one of them with the amp squared, what do we get? 0.51. Okay, so far we got this, a sum of squares of the amplitudes that we have given. So if we search for A, what we need to do is also we need to import a square root because we won't get a proper answer. Oh. So what we do to find a missing number, we subtract our total probability from all the other probabilities squared, and we get our missing number. Which is equal to 0.7. So if someone got this right, then congratulations. That's the proper answer to that question. You may notice that it's also probable to put in an answer of not only 0.7 but also negative 0.7. It also would have been a correct representation of that quantum state. So congratulations to whoever made this. Bravo. I think we can move further. So Let's move to the Q32, which is a visualization of a qubit. So here, what we are there any questions? I have seen a message in the chat, but I think it's okay. Okay. So, yeah, I didn't actually bother to code the answers for the B. But let's move to let's move further down the road. Uh, it is now a 7 on my clock. So let's finish on this in 10 minutes time, and let's take a break. That would be quite longer, I think 15 minutes. Is that okay with you? Okay, it seems that I received a couple of yes. The recordings are available at Discord. It was already mentioned a couple times. There is, I think, in announcement channel or something like that. You will see the information once you either go to I think there is even a channel specific to it. I don't want to tab out into Discord and show it. It's you can find it yourself. But it is there are Zoom links to the Zoom recordings, and then the only thing that is required is to pass a password, type in the password, but it is also included in the message with the recording link. So, are there any questions to what we have been doing so far? Because we can spend like a minute or so to maybe talk about this. Okay, I don't see any questions, so we could move further. Right. So, since we can we explored that we have for now we have been talking about a single qubit, with exceptions to last notebook where we explored an idea of having expressed more than just two amplitudes. Here we had five amplitudes, uh, five amp, right? And each of them could have been expressed as, let's say, alpha, but in this system, it was 1, 0, 0, 0, 0. So it was a five-dimensional system. But so far, mostly our um, our let's say representations involved only a single qubit. And for the remainder of today, it will stay like this. But next week we will go in further into this, and we will perform an operations on more than one qubit. But so far, we have said this. We have A, We have a, I need to click somewhere else. Oh God. Okay. So far we have said something like this. We have alpha and beta, and these are amplitudes, meaning that these can be a real value that is either positive or negative. What does it mean exactly? Well, we can, and all of these sum up to, and the squares of these sum up to 1. And if you can imagine yourself these two numbers, for example, let's say um, 1 over square root of 2. This is very hard to imagine, by the way. I do not blame you if you cannot. I can visualize this because I know, and I know the answer in my head where it is positioned. But if you cannot visualize it, then here's a basic idea how to go around this. Recall that we have we have two basis states, right? We can have either 1, 0, which is a cat 0, and we have a cat 1, which is 0, 1, right? But now what we also have compared to our regular common basic probability, uh, let's say, hmm, the basic probability, the basic way of expressing probabilities. Compared to basic way, we also have negative entries. So what I can also do is this -1. Oh, that's slightly -1. And then I have a -1 as the first entry, right? And this will be minus cat 1 and minus cat 0. Even though we do not see it in our experiment results, because there is no like classical hardware that will say us, oh yeah, this was -0. This wasn't a regular 0 that you always get, but this was -0. Well, there isn't anything like that. We cannot observe this. What we get is a squared probability, squared amplitude, which turns into probability. However, we can express this entire system as a two-dimensional plane. So here, for example, could be our x-axis, right? So 0, x, 0. There could be our 0 and y. There will be our minus x, 0, and there will be our 0 minus y. Now we can do this. With amplitudes, we can do this. So this will represent our cat 0. This will represent our 1. This will represent our -0, because recall that we could also come out with this negative sign outside of the vector. The -1 could be a scalar that scales entire 0 state, right? To 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 denote the polar opposite of our regular state. And then the last one would be our negative one as a negative ket one. And since what we limit ourselves with is in addition to that representation, we say that both of the squares have to sum up to 1. Oh my God, I repeat this mistake every single time. What we can see after we pick many different possible random combinations is that we actually land on a circle. And this is not a fluke or not some sort of, let's say, coincidence. This is how we pick the state. This is how we deal with this situation. This is what we do. So here are all of the possible states. In your Q32, you probably do not have this answer, but because this is as a task. However, here's the mostly probable outcome that we could say. First of all, we can express in general our state as cosine of some angle, let's say theta, and then sine of theta, where theta is some sort of random number from negative to positive pi over 2. And this is, okay, I will write this. Yeah. So this is what we end up with if we express our quantum states in this form, right? This turns out to be the generic form of how we can express any quantum state here on a single qubit. So, so that notation is also very important. And this is something else that you couldn't possibly get on a classical hardware, because on a classical hardware, you have either 1 or 0. There is no in between, as I have told you previously yesterday. So there is no in between. There is either 1 or 0. Okay, someone is drawing on my screen. Right. So yeah, that's a really important consequence of our choice of coordinate system and of the physics that we deal with, pretty much on a single qubit when we operate on a single qubit. Okay, so this next lecture, this Q36, I am going to present to you after the short break. I think we could take like 15 minutes. So go grab something to drink. We will meet again at let's say 1935. Is this the right hour format? I am now talking. So in 15 minutes from now, or 12 minutes. Yeah, something like that. So give me maybe, you know what? Maybe let's round this up to the 740, which is GMT plus 2 hours. So let's meet up at this hour, at this time, and we will talk about some of the concepts of that we will discuss in today's lecture. Okay, is everyone back at the computer and ready to listen to the last part of today's lecture? Okay, so I don't see anything in chat. So I think we can start again. Okay, so I will start with slight digression. And this will be, I'm sorry for the very bright flash that just happened. But let me digress for a second. So imagine that you are at night, yeah, that you have been transported back in time to 1922. Um, we don't know anything about the quantum yet. And what is the idea of that era scientists on what is the composition and the nature of atoms and so on? There was a start of the dispute on the nature of things, and one of the experiments, which is called Stern-Gerlach experiment, was designed to actually decide whether the model of atom that scientists at the time had is true or not. Uh, and it turned out that the Bohr model of atom was incorrect, partially because of this exact experiment. So what was the idea? The idea is that when we shoot a silver atom at the apparatus that has a non-uniform magnetic field, it should deflect or bend the trajectory of the atom in space while traveling through this apparatus in some way. We would say that this could be a uniform because at that time, because the atom was believed to be like a little tiny magnet. This one electron that was unpaired on the last shell in the Bohr representation, it's supposed to act like this little tiny magnet. And whether its orientation is up or whether its orientation is slightly to the left, maybe slightly backwards, when we shoot this slightly backwards, a slightly backward oriented atom into the apparatus, what we would observe is that okay, the orientation did not change. So my atom has landed here, for example. Or if it was perfectly oriented, let's say up, it would land up. And this thing the actual expectations and the reality of the results of this experiment uh, actually blew mind the scientists at that time. What happened? Well, the only thing that happened is that after shooting a beam of neutral atoms, the uh, let's say the atom flew only completely up or completely down. There was nothing in the middle, nothing even slightly down or slightly up, nothing. There was either just up or just down. And when you notice this, uh, this thing, uh, it is only a binary decision, right? But what was the state beforehand? What did we start with? Did we all we were we also where we sorry, did we always be in an up state or always be in a down state or something else? Well, it turns out that what we express during the actual like calculations and stuff that we do on the quantum hardware is that we manipulate the probabilities. But after this manipulation, let's say that we apply this matrix as we do classically, right? We have classical state, we are happy, we want to transit from 1 to 0. Then we apply some matrix and we have this state, right? 0, 3, or and 0, 7. Well, it turns out that we cannot really express it like that, right? Because what we have is after measurement, which in our terms, which the terms of this Stern-Gerlach experiment would be to fly through this apparatus. After this thing, we collapse onto either 1 or 0. There is no in the middle. And even when we have 1 over square root of 2, 1 over square root of 2, there is no way to check, to probe, like to put a hand in the quantum machine and say, hey, what are you at this very moment? I need to know. Are you square root of 2? Well, we cannot really say that. And we cannot call our IBM employee to say, hey, is my quantum state at this state? Uh, that's not how it works, right? And uh, there is a terminology to express this problem, or rather this unique position in which our state is, and this is term called superposition. So in this state of superposition, it could be either or. We do not know until we perform a measurement. Right? So we can, until we perform a measurement, we can apply our quantum gates in series or in parallel on many different qubits, as we have seen in the first day, where we declared that, okay, now we have 4 qubits, and then, for example, we apply 1 X gate on the first qubit, 2 X gates or the third qubit, using tensor product because we can isolate a single operation on a single qubit, but like that, right? We apply identity on every qubit besides or instead of any other operation, and then we apply like our choice of matrices on this one qubit that we decide that we want to operate on. And until the measurement happens, the entire state of on our quantum hardware is being expressed as a superposition of many different states. On in the case of a single qubit, it would be only a 0 and 1 because we have single bit of information. But in other situations, it could be, for example, 0, 0, 1 with some alpha plus linear combination of beta with some other state, let's say 1, 1, 0, right? It could be any combination of states and any combination of any number of bits, quantum bits in that way. So, so that's one thing. Another thing is that we could say that the Hadamard looks really weird. We said that classically we would expect something like a matrix with only positive entries, right? Because that's what we want. That's how we expressed our previous sunny and rainy transitions or fair coin flip. Uh, Here we have this negative one. And it turns out that it also has its own meaning. And it is that it happens so that some transitions act uh, on the amplitudes to destructively, and some uh, act together to, as we can see here, interfere constructively. And this is the key idea of operations on the amplitudes, that as we can see here, if we operate, let's say, on photons in our quantum hardware, that would be the case. That let's say a gate, or for example a polarizer inside of this hardware would be would interfere either uh, constructively or destructively with our current set of states. Um, then, since we have a probabilistic state, we obtain the measurement afterwards. So, uh, so that's that. And I'm sorry. And then what we have here is exactly this result. So now we can move on to the notebook Q36 and Q40, so operations on unit circle. And there is a certain thing that I would like to show you, and this is about construction of the other gates. And this is the today's topic, today's original topic, because previously we had finished our original topic, which was from yesterday, and and we will say, and we will see different operations that could enhance our quantum computing capabilities, not only beyond just regular coin flipping, but also to other states that are not that trivial to express. Again, recall that we have expressed our state prior to previously prior to the break on the circle. This circle is of a length 1 out of every single state is away by 1 from the center, because this is our probabilistic state from our amplitudes, from our squared amplitudes. And what we can see is that after applying a gate, we could express our state as a vector on that circle, and this would be the representation that we will use throughout this course. So this representation on unit circle will be valid throughout the QBronze. There are other representations, So for example, notice how I mentioned that in Stern-Gerlach apparatus, you had a up state or down state, right? So these states are not exactly, even though we say that, you know, the up state is a vector that is 1, 0 vector, right? And the down state is a ket vector that is 0, 1. When we perform our inner product of these two states, inner product, it will turn out that the result is 0, meaning that they are 90 degrees apart, right? But in the physical space, we see something different. That if we had drawn the circle on the detector of this Stern-Gerlach experiment, we would see that there is a 180-degree angle. So there is certain doubling relationship between the physical space and our state space. And this is very common to represent the quantum calculations. And the same is true if you think about the light polarization and the effects that happen when you apply different polarizers onto the light. Um, I have mentioned Eigenkreis. At the beginning of the course. He has pretty much excellent excellent series of videos about spinors. And this is exactly the way that this is exactly the mathematical construct that express this situation. And what he does in his series it is that he goes way deeper than we would be doing here or even in the Cunicle. So what we can do as well is that we could represent the situation on something like this. This is called the block sphere, and this represent different axes in three-dimensional space. And as you can see, there is a 0 vector, 0 ket, and 1 ket at exactly 180-degree angle away from each other. So keep in mind that in the QBronze, what we would be using is this. Imagine yourself a plane that would cut through this block sphere like this and only represent the axis that goes through X and through 0 and 1. This will keep all of our results being real valued, okay? Compared to what you see here, where you also have an imaginary component, because what this represents is the entire space, including the phases and the imaginary components that involve different rotations around different axes. However, what we will be using is partially some axes that actually interact in this space. For example, you can see that there is a Y direction, right? And it actually pierces through this this entire block sphere. So what we will do later is we will rotate around these axes. Even though our representation on the unit circle that we have in notebooks doesn't involve any y-axis, and the axis here will be called slightly different. It is actually the real reason why we would be, for example, applying a rotation around the y-axis like this. And this is going to be the subject right in like 10 minutes. However, however, to recap what I have told you about right now, we have different representations. We have the representation on a block sphere, and it looks like this. And there is way more information that can be encoded and obtained when using this representation. And there is also our representation that will be used throughout this QBronze. And this is representation on a unit circle. And if you will have any question during the solution of your assignments and so on, uh, always recall that we will be looking from this perspective, the perspective of the unit circle. Okay, so the one representation that is here, so the block sphere is extended representation. You can kind of like internalize it like this, but we will be using a simplified representation, and this is the correct one to use throughout the assignment. Okay, and all the further implications and all the further operations will be it will be keeping in mind with this exact representation on the unit circle. Okay, so uh, if we have now the if we have now talked about these representations, let's open up a Q40, also operations on the unit circle, as I have it here. And now uh, let's draw a couple of these states and the transitions on that on that unit circle, on that representation. So here in the first task, in the first scenario, we draw a cat 0 and cat plus. These representations turn out to be here. So we land on, I don't know why it does it, why it does that. We land on actually pretty much uh, on the axis that looks like y equals x. And our 0 is what we have previously said. So it is on the x-axis. So what we can say about these states? Well, recall that we have actually said that we can get a plus state by applying Hadamard so we will go through from the back. So we can get to the plus state while applying a Hadamard gate from 0 state. Okay, so these are the two states that you see in this first scenario. What's the next scenario? Well, now again, we see a state 1 and state minus. So also recall that what we said, that a minus state is obtained also through a Hadamard gate, but from a state 1. So that's quite different, because when we started from 0, if I was to draw this state, where do we actually land? We land somewhere here. This is our plus. And when we start from 1, we draw we get the minus also by applying the same operation. It turns out to be that on our representation on a unit circle, that there is some sort of predictable way of seeing where we land and where we start with when applying a Hadamard gate. So what we could say is that actually what happens is that our Hadamard gate in our representation is a reflection operator. And where do we land? Well, this is our axis. I will actually draw it with yellow. Oh no, it dies out. I'm sorry. So I will draw it with the blue line here. So maybe slightly less inclined. This could be very well. Okay, so the blue line is our Hadamard gate, and it turns out that it's actually exactly this. So what we do here is pretty much we draw arc prior to our gate, and then we copy the arc on the other side, and we arrive at the plus state if we start from the state 0. If we start from the state 1, what we get? Well, if we draw an arc that goes from state 1 and copy the length over to the other side, we land exactly here at the minus state. There is also a possibility that, well, we don't have exactly perfect state like this. For example, let's say this state. Where would we get over? Because we start over from some state. Cos theta, right? And sine theta. So this is our generic representation of a single qubit. So when we apply this state, when we travel the arc over here, we see that we land very close to the 0. Not exactly at 0. We will still have some counts that contribute towards the 1, but not that many. It's not exactly the same situation as we had with 1. So yeah, so that's one. So that is the representation of our gate and its actual geometrical meaning. It is a reflection over some axes that we can probably poke at if we arrive closer and closer towards this side. And what if we have a state that represent actually this state? Uh, what would we do if we apply a Hadamard gate? Well, it will be as if we never applied anything. And these special states, these special vectors, are called eigenvectors. These eigenvectors are the vectors that doesn't change under the operation that they express. So there is a formula for it on how to calculate this representation. And I actually calculated this for that actual representation, but yeah, I think, yeah. So that is what you do. For example, here we have a, we try to calculate, oh, I literally cannot open this in Photos. Where is it? Yeah, here it is. Okay, so here, oh wow. Okay, I don't, okay, so I will probably need to go to my workshop all the way down and paste it as a photo. That's what we will do. Then we will try a display mode. Okay, something happened with my software for drawing, I suppose. Let me restart it quickly. I'm sorry for the problems. Okay, there it is. Okay, so uh, this is pretty much the way of how you would calculate the eigenvector for any gate or operator, in general, any matrix that acts on some vector, because this is general math. We have a certain operation that we have to obey. So our operator, which is M, acting on our quantum state, should equal what we say lambda and the same state. This is how we calculate and this is how we obtain our eigenvector. Since the M and lambda are known, here I put a my eigenvalue is expressed clearly as 1 here in plain. Usually we would skip it, but here I paste it as a known value. We then follow our equation, and we get this ratio, which is alpha multiplied by square root of 2 minus 1 equals beta. Alpha and beta are our our vector components. However, what we know also is a second equation, which is our alpha squared plus beta squared equals 1. And this is what gets us the actual value. So this is what gives us a ratio, which is the ratio uh, of the angle, let's say, at that the gate makes with the x-axis. But then what we would like to have is, for example, a state which is intersecting with our unit circle. And this is what gives us the actual value. What you can also do is, yeah, so this is a partial proof. For example, here I type in the same vector, right? And get one of the vector components back as pretty much an old component. I didn't do it for the other one. You could do this for yourself later on. But then there is another proof for you to prove that you could also do the same thing in the other direction. So this is one eigenvalue from what I have shown you. But when you draw the Hadamard gate, you also see that after you make this one, after you find this eigenvector C, there is also its negative component. There is also its negative, and it also won't be changed by the by applying this gate. So this is very short introduction to this. There are more. For example, we could do the same with the X gate and other gates that we have just thought about. But there are other kind of gates. But there are other kinds of gates. This one was a reflection. Why do we say that this is a reflection? Well, we could recall the fact that when I applied H on the zero gate, I got a plus. But after I apply H again at the plus, I got 0. No matter how many times do I apply H gate onto some state C, if I apply H gate twice, it is as if I didn't apply anything. So this is also connected to some other property of the quantum gates, that some of these gates are their own inverses. So this is also another property. And we say that in this case, it is also its own quantum conjugate. Because recall what you can do with this. There is 1 over square root of 2, 1 over square root of 2, 1 over square root of 2, and then 1 over square root of 2 with the minus. So if we had to calculate the complex conjugate transpose of this, so this is a regular H. If we were to calculate complex conjugate transpose, we would get the same thing. And this is really, we could see it actually with our bare eyes, because if we transpose, which means we pretty much replace the diagonal components, the anti-diagonal components with themselves with when we swap these. Oh, I have actually have removed everything. And then what we did is to calculate a complex conjugate, which we could say there is this plus 0i, which becomes negative 0i, which is meaningless. Then we could say that yes, it is actually its own quantum. It is actually its own complex conjugate transpose. Oh my God, I'm sorry. I wanted to see this. And we actually want to choose gates like this. Because what we do is we deal with the probabilities, and all the probabilities, the actual length of the vector after each of these operations have to stay the same in terms of the length. It has to stay the same. So what we do is we pick these operations to be unitary, and we also try to pick the special unitary. And in terms of special, we say that their determinant would be 1. Which means that the determinant, if you recall or if you watched, if you didn't, I really recommend you to watch. There is a nice series from Free Blue and Brown. What we say about determinants in terms of the geometrical meaning of the matrices is that the determinant determines the scaling factor of first the vectors, and second the, let's say, areas of objects in the space that we operate in. Here we operate in the actual like two-dimensional space. If we had something with determinant that is greater than 1, we would stretch the vectors and we would also stretch the areas. And we don't want that. We don't want to go out or even shrink the probabilities to be like 0.9 or 0.1 or even greater, like 1.1, 1.2. We would like to keep the results equal to 1. So that's why we pick these matrices to be exactly like this and not nothing else. Okay, so what are the other operations? So I told you about the reflection operator, which kind of like mirrors this vector, and it reflects it on the other side, intersecting it with our unit circle. So what are the other operations? Well, what about something that actually moves me a tiny fraction, tiny bit, right? And what if I wanted to apply this operation several times? Well, this is exactly uh, the best accomplished by rotations. That's the other operation that we could do. And uh, and the rotation, well, we could say that, okay, I want to move from the minus, and recall, Matthew, that you told us about linear combination. Very simple fact. We could move from state minus all the way to state 0 by just throwing in this vector that I have just constructed, right? We could even try and calculate its x and y. and we could apply it like this. Where would we land? Also on unit circle. So why wouldn't we just say like alpha, beta, plus x, y equals 0? Why wouldn't we just do this? Well, the reason is very simple. We would like to have a repeatable operation. And once we define a gate as a matrix that has, for example, like a representation like Hadamard gate, we could very easily apply it over and over. And when we have this single vector, well, okay, let's say I would like to go from this state now, and I would like to go exactly the angle that is expressed by my arc that I have just drawn. I will draw it in a quite different angle than this, right? So I would like to move here. I have come up with this vector. But what if I now wanted to use this vector somewhere else? Well, it doesn't work because now here I am out of this vector, out of this circle. I have violated my equation that I all at all times I would like to obey, which is alpha squared plus beta squared equals 1. I have just invalidated this. So that is why we stick to also gates that are either reflections or rotations. One of these rotations is expressed. Here is also a quantum state. You could, at your own leisure, you could review this after we finish the lecture. We could apply the rotation with the operator that I have told you about during the review of the Bloch sphere. So that's why this rotation as applied over y-axis, because we don't see from our representation on a unit circle that only involves real numbers. That is why we have this y gate here, rotation y gate. Okay, and if we want to rotate, we have to pass in the double of our angle. There is a general version of our gate. So for example, here I will apply it. Here, as you can see, our Matplotlib library helps us and draws us what would be the rotation. Inside of the box, there is an angle that is displayed. And what happens is that after our rotation, look, we can get some other, yet another, let's say, state that isn't really a fair coin. In this sense, it would more than the fair coin, it would represent our biased coin. That would, in this scenario, since we have 2 pi over 3, this would be, we could also see this and this. This would be more like, I think this would be, oh wow, sorry. So pi over 3 is would be this angle, right? This would be 2 pi over 3. Am I actually right? Where was this? 4 pi over 3. Yes. So we applied 2 pi over 3. In this gate, it actually showed 4 pi over 3. And this is what we applied. So this is how you can get to the state that isn't exactly the fair coin that you want. Uh, the fair coin, if the fair coin isn't what you want, this is what you can do. And the difference between reflection and the rotation would be that after applying it several times, so let's say, oh my God, it happens again. Uh, I think I just scroll on my scroll wheel on mouse, and this yields a slightly thicker line. So if I apply this in series, and I will multiply my state, what I would do after what I would see after each of these rotations is that I move at exactly this angle, and I would get closer to 1, then I would get out of the 1 into the zeros, then into the 0, and so on and so forth, and so on and so forth. So that is how you can also see the effect during the experimentation with different quantum states in the simulator after you construct the circuit. So here's operation again. You have to apply not y gate but ry, which means rotation y, and then pass in double your angle. Right? Since yeah, there are, here is I think the generalized formula for this. Okay, yes. So this is what you would get in your representation. And this formula comes up from linear algebra. If you would have, for example, try to come up with this formula yourself, it would be like this. So you have some matrix, right, that with unknown components that acts on my state, which is a cosine theta, right? Sine theta. And what I get as a result is a cosine theta plus some angle alpha and sine theta plus some angle alpha, right? So this would be the equation that would end up giving you the actual matrix that you would that we see here for the rotation. There is also a matrix for the reflection in the second notebook, which is Q48. So about rotations, it is Q44. About reflections, it is Q48. And so the exact formula is here. So here it is with the double angle, and there is also a difference that the negative sign is at the diagonal. There are cosines, sines, and in terms of the actual rotations, well, this is the same, but the minus here is on the first row, second column component. So that's that. Yet again, we have some other reflection operations that we could discuss. For example, what we could say is that I actually have this prepared. So let's say stations. That it? Yes. So I have slightly expanded on the drawing capabilities of this workshop myself. So if we can see here, it is also drawn in the Matplotlib. So recall our reflections. So the X gate could be said to be reflection over the y equals x, right? So this is X gate. And this makes sense since 0 turns directly into 1. But also what we could see is that the minus plus would turn into a regular minus. And the actual equilibrium state, which would be our plus state, for example, would be the state which could be expressed otherwise as an eigenvector. We could test this right now. I will go to the probabilistic bits. No, not probabilistic bits. Qiskit start. Recall this notebook that we have been. Recall this simple program that we were operating on previously. So I will reverse these operations. And what you will notice is that the X gate had absolutely no effect. After we apply the H gate, the X gate had absolutely no effect. No matter how many times I append this operation, it won't have any effect. Not 1, not 2. I have also the same amount, the close to perfect fair coin. In actuality, this experiment, this series of experiments, because this is also simulating some of the quantum randomness and uncertainty. You will not get absolutely perfect distribution because all of this is probabilistic, right? It could be that uh, exactly as when you have flipped the coin, right? It could have been that after you collect entire set of your experiments, it would have been that you had 10 more tails than heads and so on. So you will never get a perfect distribution. There is a way to freeze this, and there is a parameter which I completely forgot today, but there is like simulation seed. I have no idea if there is a parameter that we could see here. Sequence run options. I think it won't tell me. So I won't waste my lecture at this thing. But there is a simulation seed parameter. You could go to the Qiskit docs and look it up, and this will act as a, for example, from random import seed, and it will give you the same distribution, the same result at every single time you perform the experiment. I will get back to this in the next lecture next week, and I will provide this for you. So if you want find this, I will include it in the next workshop, so that we could have some comparable results between each other, and you will have the same results as I do on my end. I will, for example, freeze the simulation uh, at this exact seed, and you could do the same and see if results match. Um, so that's also a possibility. One is that you could seed, for example, you could seed also from NumPy and from the regular Python, but seeding from a regular Python doesn't really work. You have to provide a seed into the Qiskit library itself. And this is the way to do it, by the parameter in the run option. So that's the slight digression. And coming back to our reflection operators, we have two more apart from Hadamard. I have told you about just now. I have told you about the not operator, which is a operator that reflects over y equals x. And there is also a z operator, which acts like reflection over x-axis. So, so these are two gates that we actually will use. The z operator will come up later on. And this is the reflection gate formula that you can use to uh, to to express the reflection on the unit circle. I think I have mentioned everything that I wanted to mention today. We could go over something else if you have any questions. Could also run again the rotation so you can see the axis again. Oh, stop and rerun. Yes. Okay. So these are the gates that we use in the reflections. So reflection 1, the H gate is yet another reflection, and the X gate is yet another reflection. And there are also states which you could see. So the plus would be an eigenvector of the X gate. The plus state would express this situation. Okay, so are there any questions to today's lectures? I don't see any. We could also express the rotation. So this is also another way. Since so that's an extra. Uh, so there are more than one simulator available at the from the um, let's say from the Qiskit. What you can have also is something that is called, apart from Air Simulator, I mean, these Jupyter notebooks that I am going through are standard material from the course, from the QBronze. Or what? Or do you mean what exactly do you mean? Because I am probably think that you mean these programs that I wrote myself, which about these are not available for Discord. The programs that are available from Discord are the actual Jupyter notebooks, which are pretty much standard material that you are welcome to interact with. And these tasks that I have presented to you and these notebooks, right? For example, here, this notebook from Q40 operations on the unit circuit, these are standard notebooks that we have linked and we are going through. And this is the course material that we progress through in this QBronze. So in other words, these notebooks are standard material. The my programs that I show you through the um, through the PyCharm are not. These are not standard. Yes. So one extra information is that coming back to our to my program that I have prepared is that the the other the added information is that there are more simulators. For example, you have something that is called state vector simulator, and what it does at its core is doing exactly what we do manually in code by performing these operations of rotations and showing where showing, for example, if after cat zero, if after I apply age gate to state 0, I get a plus state. So the plus state, recall, is 1 square root of 2 and 1 square root of 1 over square root of 2. And this is the representation of the vector. And this state vector simulator calculates exactly these transitions. And it shows us what would be the result, what would be the quantum state as a result of preparing our circuit and performing all of our operations. And here I express only a real part of this, of these calculations. And what I do have is this. So after I perform rotation, I rotate my state vector. So this is angle 1 times pi. I obviously did not shorten this notation. I'm sorry. Um, so I applied here, I apply at first rotation, second, third, fourth, and fifth. I apply a pi over 4, then 2 pi over 4 uh, as a 2 times the rotation, right? So this is a 1 rotation. This is 2 times rotation. This is 3 times rotation. And this will be a 3 pi over 4, and so on and so forth. And what I have in my state vector is this. So after 1 rotation, I have in my, as my state vector, I have 1 square root of 2, 1 square root of 2. In a row representation, this would be this. Then after second represent, then after applying second time my rotation, I would end up having 0, 1 in a row notation. So this would be my state 1, and so on and so forth. So you can express using state vector simulator, the program, the Qiskit, can do the calculations for you. And it can express the final state that you should observe during your quantum calculations, right? Before the act of measurement. Because after the act of measurement, what you would see is the distribution. So for example, something like this, right? But before, if you want to recover the state, recover and get the actual amplitudes, the state vector simulator allows you to do this, to peek onto your quantum system during the calculations, or in the middle of it after you apply some operations. Keep in mind that this also is only on your hardware. State vector simulator is not available to be had in the actual quantum calculations, because if it had been, then we wouldn't worry about this, and we wouldn't worry about, performing hundreds of thousands of different experiments and recovering the distribution from these calculations, from performing these experiments. And then, based on the results and based on the distribution, we would recover this state. No, we cannot do this here. We have to go, unfortunately, with the hard route, right? So that's that. But the state vector will help you understand what happens with the amplitudes. That's the main benefit of that. And it also could help you develop new algorithms, for example, to double check whether you land on a proper state or something like that. It could be a uh, good, uh, let's say, variety to test against, and not only obtain counts every single time, because they really don't tell you about, for example, the negativity of the amplitude. The 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 results of experiments do not tell you about this. We will get to it, how to obtain it from the actual results of experiments, and how to perform an experiment to actually obtain the information about whether we land in the negatives or not, but this would be in the next week. And before that, you could use a state vector simulator to obtain the amplitudes, right? So that's the end of today's lecture. This was the extra portion. I think in QBronze it is mentioned what the state vector is doing, but slightly later on. However, I would, since we have mentioned about, since we have talked about the representation of a unit circle, this directly connects to our today's topic. Okay, yeah, so that's it. Thank you for joining today's lecture. I hope you gain some nice insights. I will explain to you later on in the next week this one program if you want what I do here. But this is slightly more complicated, and also we will use a conditional gates in the next week. So don't feel discouraged. Don't feel like you miss out on something. We will get to this.
Mm-hmm. Great. Thank you. Thanks, Mateusz, for the presentation. Uh, all right, so that was the third day and third session of our workshop. We'll continue on Monday. Um, there were some questions about the QInten program and some other opportunities, some next opportunities um, for learning and gaining experience. If you review our Discord server, you will find an announcement about the quantum machine learning workshop, which is another quantum computing workshop that we organize. So it will be on next weekend, next Saturday and
Oh,
Sunday.
okay. Can I interrupt you?
Yes.
Because there was a question about how do I initialize R simulator in
Ah,
Qiskit.
sorry.
So, and I didn't answer this question. I'm sorry. So I will answer it now. If you are here with us,
Okay,
Adriana.
that's fine.
So as you can see, what I do here, I have three different imports. These are basic imports. This one, the from Qiskit result import result, this can be completely skipped. This is just for me personally to type hint in Python and to get auto completion. But in basic thing, what I do is for air simulator, I need just to import it from Qiskit Air backends Air simulator. This is the new way of doing this. I think that in the workshops um, inside of the actual workshop Jupyter notebooks, this is simplified to from Qiskit Air import Air simulator, and then what you do is you run a job like this by invoking Air simulator plain like this. You just kind of like making an object, instantiating the simulator like this. Then you invoke dot run with the number of shots, and that's it, pretty much. And this result, uh, what I have imported here, so this would be like from something something import uh, result, right? This is this entire object is the result object, which you then reclaim counts from. And this is the exact result of our simulation. So in short, you import an air simulator from Qiskit Air if you operate on the version 1.2 or 1.x. if you do this from the version 2.x, then that's what works for me. So from Qiskit air.backends, because there are collection of backends, uh, you find this module Air Simulator and import it from there in the second version of the library of the Qiskit, because there are two now, right? There's 2.2, which is the most, like, this is the most fresh. So I give it to you, this information for you if you wanted to move on with this, for example, to interact with the new version. So that's the new version. So you invoke, so then you invoke it exactly the same way. So you call it, you make an object out of it, and then you just run the simulation from this. Is it clear now? Nice, thanks for confirmation. So that's how you do it, right? I will actually, yeah. Okay, so we can wrap up.
Okay, thanks, Mateusz, once again. So before I just wanted to just recall that we've already announced the quantum machine learning workshop that will be held in the next weekend, October 11 and 12. So you can still sign up if you are interested. And within the next few days, maybe even tomorrow, we'll announce the QPoland Global Quantum Hackathon. So it will be on October 18 to 26. It will be online only, so you can also participate and you can already practice your quantum skills by solving challenges proposed by our partners or developing quantum games or some other quantum projects. So last year Mateusz was one of the winners, and now you can see this year he's already an instructor in QBronze. So great career, Mateusz.
Yeah,
Congratulations.
yeah.
Yes, so there definitely there will be more opportunities. So on Thursday, I think I also announced it. If not, then maybe I'll announce it soon on Discord. That on Thursday there will be also next episode of the Warsaw Quantum Computing Group meetup. It's online only, so you can also sign up and participate. But I'm not sure you'll learn much more about the quantum computing, but maybe a bit more about the general quantum computing ecosystem, like about different technologies, how to build quantum computers, the bottlenecks, different applications of quantum computers, the general quantum worldwide ecosystem, and the ecosystem of quantum technologies here in Poland, which is growing quite fast. So yeah, I will introduce it on Thursday. And there will be some next workshops in the next few months. So in November, we'll organize QSync, so it will be a workshop on quantum error correction. In February, there will be a QSilver, which is a workshop on the Shor's algorithm and quantum Fourier transform. In March or April, we'll have workshop on which QNiCal, which is focused on oracular quantum algorithms. So there will be definitely more opportunities to learn, to gain more knowledge and experience in quantum computing. All right, that's all for now. Thank you for joining the session. Thank you, Mateusz, once again for the great lecture. Have a great weekend, everyone, and let's talk again. And hope to see you on Monday. There's a question about the hackathon. Yes, so not necessarily. So you can also participate individually, but there could be teams up to 5 people.
So from my experience, I didn't have a team, and we just like found a group, a bunch of people together, and we participated together under the for the quantum open track. I did make a quantum game, but I thought it would have been better to make it as an open track. Yes, because my reasoning was that the most important part was actually to develop a quantum algorithm, and the quantum and the game part was like only a front end to show how it works actually. And it was just a bot for that the quantum algorithm controlled a board and was your opponent.
Mm.
So that was my aim, and this was, and it turned out to be pretty much um, a success. It worked. So this is why what also won at previous quantum hackathon, because what mattered most is first that it works and it does its job. And if you can achieve this, then you are already ahead in terms of other participants. At least that was um, my experience from the last year. So if you can deliver something that is really nice and works, the most important thing is it works, it executes, it performs these calculations on the quantum, let's say even a simulator, because what I did is I didn't connect to any IBM cloud or something like that. Uh, we did we did invent some sort of a way to perform a calculation on quantum hardware that would control a board in checkers. So that was the main point for me to do this. And it worked. It worked. It worked through the algorithm that was Grover's algorithm. And we searched through the collection of allowed board moves to determine the best move possible, right? So that's what so that was the solution to that. Yeah. So that's the most important thing. First, to find the nice application. It could be even this as simple as that, but make it work.
Hmm.
That's the most important thing, I think.
Yes, but anyway, you should register individually, and then you can. But you can try to find some team members earlier. But anyway, everyone has to register individually, and then just announce the team once it is formed.
Yes, there was a channel
Yes, there will
to
be there will be
find
a
your
channel. Yes,
partners,
find the team. Yes, so you do not have to do not have to have a team
and
now
I use that
during the
channel.
registration. Yeah. Okay, good. So yeah, as I said, we'll announce it within the next few days, probably. Thank you once again. Have a great weekend, everyone, and let's see you, talk to you again on Monday. Bye bye.
Bye, see you.